Okay, perfect. Good morning, everyone. Welcome back to this new webinar on our energy data and modeling program track. I hope you can see me and hear me well. If it's not the case, write in the chat so that I can fix any issue we can have. So as you know, today we have with us some partners from Politecnico di Milano, which is the leading technical university in Italy. So we have with us Nicolò Golinucci, Francesco Tonini, and Nicolò Stevanato. I will just do a brief introduction and a brief recap, at least with respect to our agenda, and then I will leave the floor to our partners for today. So, as I was saying, today is the 10th lecture. The topic will be again on modeling, but you will have the opportunity to have these lectures from our partner and to see how modeling is applied in real life in a specific project they will talk about. Then we will move Thursday, we will have a peer webinar with the Imperial College, so another university which is a partner of us. And then next week we will have the SDG7 lecture and the solid biofuels estimation model lecture. And then the next one we will wrap up this webinar series and close the session. You will have the opportunity also to give us feedback on how this program was, etc. I just remind you that if you have questions, you can write in the Q&A session, in the Q&A box. So we will periodically look at the comments we have, and we will ask our partners to answer them. On the other hand, and probably it's the best way actually, I suggest you to raise your hand through the Zoom functionality so that I can give you the floor and the possibility to unmute yourself and also turn on your camera so that you can directly ask for any question you may have. So without further ado, I will leave the floor to my colleagues, and I stay here for whatever needs you may have. Thank you very much.
Thank you very much, Darlene, for the introduction. I'm Francesco Tonini, a research fellow and I'm bringing also you the greetings from Professor Emanuela Colombo, our research group leader. And she leads our group in which I work together with Nicolò and Nicolò, and we are bringing on some research activities on energy modeling. My duty for this morning is to bring you a very short introduction about the perspective, let's say the perspective of our approach in energy modeling. I will start by bringing on the table some of the challenges that are related to energy and development, and then I will provide you a brief overview of our modeling suite for tackling those challenges in order to provide policy and decision makers with some insightful information and tools in order to design policies. Energy is at the center of current challenges, and this is highlighted by the fact that together with Agenda 2030, UN brought energy along with other issues with a specific goals in the new definition of the Sustainable Development Goals. This was not the case of previous agenda, the one related to Millennium Development Goals. Energy is crucial for socioeconomic development, and we will see further insight about this. But energy is also a matter of quality of life, a matter of energy security. And we in Europe in current days are living it with a strong momentum. And also, of course, energy is related to environmental protection. And this is highlighted by the several steps that in the international path toward the sustainable development as defined. As I told you, energy is at the center of Goal 7 of the 2030 agenda, but energy was at the center of the debate also during COP21 in Paris and the other meetings that started from that time. And energy, and to energy, it was devoted also a specific topic for the 2012 Sustainable Energy for All here. And this is because we as a humankind are nowadays at a urgent turning point, because it is in front of us the evidence that sustainable development will not occur without a decrease of natural resources consumption and with a decrease of waste production and production of emission. Nevertheless, a sudden shortage of energy could put under severe threat our societies, our life. Therefore, there is the necessity of finding a new way for providing energy for all in the future. And to depict this path, we have to look to the sustainable definition, the sustainable development definition itself, that provide us with a triple dimension according to which we have to understand the reality in which we are living. And so if we start from the environmental dimension, we have to deal with the constraints that the universe gave us. Me, Nicolò and Nicolò, are engineers, and the first things we had understand during the university courses is that the second law of thermodynamics cannot be overcome. It means that we have to take in consideration the fact that our activity in our life has consequences, irreversible consequences in terms of resource consumption. And this means that we have to take into consideration the boundaries of our environment, and a growth with unconstrained consumption of resources is no longer acceptable. Then there is the socioeconomic dimension, and I will start with the economic side of the story. In this graph, you see the correlation between the total energy supply per capita that you have in the x-axis that represent somehow the energy availability for a country, while on the y-axis you have the gross national income per capita that represents somehow the welfare of a national economy. And as you see in the bottom part of this graph, there is a strong correlation between those two variables. With the bubbles, you have all the countries in the world, And those are differentiated accordingly to the World Bank clusterization into very high human development in red, high human development in yellow, and in blue, medium human development countries. So for medium and let's say the first part of high human development countries, you see that the correlation is very strong. And this means that the provision of an additional ton of oil equivalent to the country, it means an increase in national income. So for those countries, energy is a leverage for national development. But after a certain threshold, we see that the correlation becomes weak. The bubbles are sparse. It means that other dynamics occurs, and the socioeconomic development is due to other factors. For example, if you take a country like Italy in Europe, if compared to US, for example, has more or less the same economic status. Our average income is more or less the same of those we can find in US. Nevertheless, the energy consumption per capita is very different. So for very high human development countries, other factors have to be taken into consideration. For example, the behavioral choices of people, and also the tendency of using energy efficiency measures. And coming to look at the correlation between, again, total energy supply and the Human Development Index, we see that this issue is even stronger. First of all, I would like to remember you that the Human Development Index take into consideration, together with the economic factor, also other factors related to education and health. So in a certain way, these indicators bring a measure about the quality of life of a country. And you see again that for let's say medium and low part of high development countries, the correlation is again more or less linear and very steep in this case. So again, an additional ton of oil equivalent provided to the country bring a huge development in terms of such socioeconomic parameter. But after a certain threshold, the correlation tends to reach a sort of asymptote. It means that an additional provision of energy to the country, it is not devoted to an increase in well-being for citizens. And the analysis of those factors give me the chance to highlight the issue according to which energy is not a fundamental right. Energy does not determine the human dignity, but energy, it is at the basis of all the other processes that bring to human dignity. In this way, I'm an engineer, but I like to contaminate my studies with also some thought that comes from other fields, like philosophy in this case. And so we can define in a certain way energy as an instrumental right. It means that energy, even not being a necessary condition for achieving all the fundamental rights, it is in a certain way the instrument we as a humankind need to achieve all the other fundamental rights. And in fact, energy, it is a matter of justice and rights. But if we look to the numbers, we see that our world is a bit far from achieving a just energy condition. In fact, looking to numbers for low-income countries, we have billions of people that live without access to electricity, and this number is pretty high if we look to those who still rely on the use of traditional biomass. But the issue has a different face, but is still there. Also, if we look to middle income and high income countries. In fact, we have that 1 billion people in middle income countries has not access to reliable grid. It means that perhaps they have the connection, but the provision of electricity is intermittent, and therefore it is difficult to start some economic activities that can lead to a better economic condition for the country. And the energy issue, again, in high-income countries has another phase. In high-income countries like Europe, for example, there is the issue of fuel poverty. And these issues has been even exacerbated by the COVID pandemic crisis. And with this, the definition of fuel poverty is the one according to which a person can be considered fuel poor if he has to pay more than 5% of his income for energy-related stuff, and more than 50 to 75 millions of Europeans are affected by this issue. It means that there are many families that has the connection to electricity, that has the gas supply in their house. They also may have the heaters, but at the end of the month, they cannot afford the bill. And this has a strong impact on daily life and also other issues related to health and education. So what is interesting is that UN, in defining the sub-targets of Goal 7 has taken into consideration the multiple aspect of the energy issues across the world. Of course, target number 1 is devoted to access to access to energy. That is the crucial point. But number 2 and number 3, it is more specific for medium to high development countries, where there is already the possibility of having connection in every house, but there are still problems related to dirty consumption of energy and low efficiency of devices. Then again, 4 and 5 targets are related to international cooperation. That, as we will see in the last part of my presentation, it is at the center of global development. Only through international cooperation it is possible to achieve the just energy transition that is declared by many international boards. And then we have seen that, energy is an issue, and it were an issue even before the condition we are living in our days after the COVID pandemic crisis. And this crisis brought on some of the issues that were somehow sleeping. The COVID pandemic brought out the issue of oil price fluctuations, the risk and the issue of reliability of the grid, the provision of materials that are crucial for the energy transition, especially the raw materials, and gave us the chance to understand how much is important the issue related to carbon emission. And this peculiar situation was very shocking from the energy perspective. In fact, in 2020, the world registered a collapse in energy demand that was never seen before the World War II. And this gave us the magnitude of the challenges we are facing. And this is a crucial, especially if we look to sub-Saharan African countries, where the energy issues are exacerbated by the lack of access. So if we cannot find the proper solution for sustainable pathways toward the just energy transition, the worst effect will be felt among the most vulnerable communities. So after having done such overview about the challenges, I will shortly introduce our approach here in Politecnico di Milano. Our final aim, as I told you, is to define insightful, how can I say, to provide policymakers with insightful information about possible technology development pathways, taking into consideration also the behavior of citizens that strongly affect the evolution of energy-related variables. And this is done with a specific eye to international cooperation, knowing that only with a strong cooperation between countries, it is possible to achieve the so-called just energy transition. And to face those challenges, we have to remember that essentially all the models are wrong, but some of them are useful. And this is somehow our mantra in looking at the results we obtain from our tools. And the tools we will show you during this morning can be somehow subdivided into those 3 layers, in which we have the first one, the description of the technology. At the second one, we have indeed the analysis of how a technology under study can be integrated into the reference sector, the sector in which it operates. And then in the third layer, that is the last layer of the analysis, we try to follow the interlinkages between the sector of understudy, that is the energy sector in the majority of the case, together with all the other sector of a productive economy. For the first layer, we have a software related to the definition of embedded impacts, so some software related to LCA analysis, product LCA analysis, Then we have some software related to the hourly definition of energy requirements, and other software that are aimed at the definition on how the energy demand can evolve over time. Then in the second layer, we are using some open source tools that you will see together with my colleague Nicolò Stevanato further in details. And then in the third layer, we have some instruments that come from the industrial ecology sphere that give us the chance to understand the interlinkages between different economic sectors, but you will see further details with my colleague Nicolò Bonucci. So I close my introduction giving you an overview on how putting together those three layers, it is possible to have an integrated perspective in policy analysis that give us the chance also to tackle different issues that comes from different goals of the Sustainable Development Agenda. So thank you very much. And if there are no questions, I can leave the floor to my colleagues.
Okay, thank you, Francesco. Good morning, everybody. My name is Nicolò Stevanato. I'm also a researcher at Politecnico di Milano, Department of Energy. And today I will briefly try to introduce you the practice of energy modeling, especially connecting to one of the aspects that my colleague Francesco introduced before me, especially among the targets of Sustainable Development Goals number 7, the one of ensuring access to energy to everybody by 2030. In particular, we use, as Francesco said, a set of modeling tools in order to provide policymakers with data, solid scientific data that they can use to produce scientific informed policies for their countries. Okay, so as we know, a big share of the population without access to electricity resides in sub-Saharan Africa. And the challenges that this particular problem brings along are the fact that the majority of population without access to electricity lives in rural areas. They are scattered populated, and the levels of energy consumption and livelihood standards are very low. This brings along the problem that expanding the national grid might not be economically viable. For this reason, other technological solutions and specific planning strategies are required in order to find a technical solution to this problem. Energy modeling can help supporting this planning phase. The main technological solutions to the issue of access to energy, to electricity, as you might already know, I'm quite sure, are the three I'm presenting now. Standalone solution, usually in the form of a solar home system, but can also be, for example, a single diesel generator or a mini wind turbine. are characterized by being a piece of technology that serves a single user from a single energy source and is particularly suitable for extremely isolated users with very low energy demands. Normally, the size of the generator is well below 1 kilowatt of power. Some of these technologies come with included a small battery pack for decoupling energy supply and energy consumption. What happens when the load demands are a bit higher and the community we intend to provide with energy is not that scattered? Is that mini-grid solution comes in hand. Mini-grid are off-grid energy systems characterized by multiple energy sources and connecting multiple users. They usually come with a storage system and a backup as a generator for ensuring energy supply continuity that is not granted by renewable energies alone. Normally, the size of the generating supply side is below 500 kilowatts, but we also have examples of bigger mini-grids. And let's say one of the main benefits that come along with installing mini-grids is the fact that they can support the development of productive activities. In fact, being a bigger energy system, energy supply than the standalone system, the energy produced with the mini-grid can be used to foster economical activities and productive activities. This is commonly referred to as productive uses of electricity. While of course, the most easy to think about solution is the expansion of the national grid. Is very expensive and is limited by natural boundaries, but when load demands are very high and very dense, it can be the cost optimal and technologically optimal solution. How to decide which solution to adopt and how to optimally size this solution to grant actual sustainable development to communities is something that energy modeling can help us understand. So there are different categories of energy models. All of them perform slightly different analysis and can help us answer different questions. There is no right energy model. It really depends on what is the question you aim at answering and what is also the geographical scale you are considering. Energy system models at national scale, for example, allow me to study the evolution of national electricity systems and how to optimally dispose of technology, build new technology, install capacity, and operate these energy systems, this installed capacity, in order to grant a cost optimal, for example, use of the system, or understanding how much capacity and where it should be installed in order to cover the growing energy demand of a country. The same concept can be derived for energy system modeling of off-grid systems, but in this case, instead of a national system, we are studying a single off-grid system or a mini-grid. In that case, the software can help us understand the optimal size of PV panels, of wind turbine, if it's suitable to install, how much battery pack do we need as a generator, depending on the load that we expect that the mini-grid will need to satisfy. On the other side, we have geospatial rectification models. This category of models works on very wide areas and based on geographical information systems, so GIS systems, can help me identify rapidly the optimal solution among grid expansion, mini-grids, and standalone systems that is more suitable for granting access to electricity to an entire population. So we identify the non-connected population of a country, for example, and through these softwares, we have in one single run the cost optimal solution. We identify the solution. We do not size it, then we size it with other models, but at least we identify a strategy for an entire country in one single run. As Francesco already introduced, in our group, we work at 3 different layers. I am going to talk to you about layer 1 and layer 2. So characterization of technology and optimal sizing of energy systems that rely on that technology. But I will first try to give you the definition of energy modeling. Energy modeling is the mathematical representation of a physical system. Since we cannot bring an energy system to a lab and perform experiments with that, we build the energy system mathematically on our computers. And with that, we can perform experiments assessing what would be the impact of policies, for example, or of shocks. We can assess how could we satisfy a certain emission target, how would the system react to a shortage of a certain resource. So through energy models, we can experiment with the energy system. There are several kinds of energy models that also vary in temporal resolution. It means that we can model phenomena that happen in minutes, like can be the variation of electricity demand of a community, or we can plan for decades. We can plan the energy system of a country for decades. And we can observe systems that from the local level up to a continental level, for example. And different models cover different geographical and temporal resolutions. Today, we will focus on models that optimize the supply generation and the optimal dispatch. So how much technology to install and how to operate it in an optimal way. The usual inputs to such category of model, that is called also energy system models, are the load demand, because ultimately my goal is always to satisfy a certain load demand, might it be a country or a community, isolated community. Availability of resources, and in particular availability of renewable resources, because they will be available differently along the year or the years. For example, solar power is available only during the day, and wind availability has particular patterns in different parts of the world. We also characterize technologically and economically our technology. It means we have to define efficiencies, we have to define costs, operating costs, installation costs, in order for our model to properly plan with our technology. And we have planning parameters such as the discount rate of the country, how many years do we want to plan for, and this category of information. Then the model itself will provide as an output the optimal capacity of the technology I have decided to model, the optimal dispatch, so in which way should I use this technology that I have installed to minimize costs, for example. And associated with this, we will have all the economic and cost parameters, net present cost, the levelized cost of electricity, and a detail of the fuel consumptions, for example, and variable costs that we will face during the operation of the system. The first thing that is fundamental to do before starting any energy system modeling is the definition of the reference energy system of the country or of the community that I want to model. So I need to understand which technologies are existing, which energy sources, and which demands I want to satisfy. This is an example for a country divided into many regions inside the country. If it was Kenya, for example, we could say, okay, we have the entire country of Kenya. And then we can characterize the regional demand of Nairobi region, of Western region, Mount Kenya region, and Coast region. And these 4 regions will have imports and exports among them inside the country. And every region will be characterized by different existing technologies, and I can plan to install new technologies in any of those regions. And I will also optimize how to use these technologies throughout the years to minimize the costs. But I'm saying continuously optimizing optimal solution. What does it mean to optimize? Optimize means basically to mathematically minimize an objective function. So I have a function that I want to minimize. This function can be the net present cost, or can be emissions, for example, or I can also be maximizing for example, I want to maximize welfare, or I want to maximize jobs that are created by my intervention. So minimizing or maximizing a function, 99% of the time is minimizing net present cost. So we deal with economic optimization, but this minimization of the system is constrained to physical behaviors of the system that I'm modeling, such as energy balance, power balance, mass balance, technological constraints. It means I have to minimize the cost of my system, but I have to respect the physical and thermodynamic laws that characterize my system. In particular, I will make a very simple example in 2 dimensions. If I have to maximize x plus y, and then I add a series of constraints such as x greater than 0, y greater than 0, x is smaller than 3, y is smaller than 4. You see, I'm starting to define a region x plus 2y greater than 2. These are representing all those constraints I was talking about before. So the gas turbine has this efficiency, solar resource is available only in these hours. To install a power plant, you have to pay such amount of money. And every point inside this region are feasible. It means all of them actually work. So I can run Kenya entirely on coal power plant. It works. It's not optimal, but it works. Then the matter is finding the optimal solution and following the borders of my feasible region. I will eventually get to my optimal solution. And in this case was to maximize x plus y. This is a 2-dimensional example. In n-dimensional example, like is the case of energy modeling, it looks something like this. This is just to give you an idea of the mathematical process that is behind optimization. Now, as I said, a large variety of energy system models exist. We like to differentiate not only in terms of temporal resolution and spatial resolution, but it's also quite important to talk about open energy modeling. Open modeling means that unlike Times, Message, or Homer Pro, that are softwares that you have to pay in order to use them, and they are proprietary softwares, meaning you have to buy them and you cannot look inside the code. A huge family of open models is now coming to light, also thanks to the Open Energy Modeling Initiative, where researchers come together to build models that are completely free online, and everybody can download them and also see the source code of the model in order to understand if they agree or disagree with the implemented equations and with the assumptions. Focusing now on one of those models, PoliMi Spy, that has been developed inside our group at Politecnico di Milano, is an open modeling tool for sizing of off-grid energy system modeling. That, as I started this brief intervention, is what I'm going to talk about today. So technologies to grant access to electricity. Now, what does this software do? it focuses on the sizing of off-grid energy systems and is usually by our group coupled with another software, RAMP, that is a software to simulate the load profile of a community. So if, for example, let's see if I can. Okay, I can simulate different scenarios of electric load demand of a community based on the informations I have on the number of people in the community, categories of users, and for every category of user, which are the appliances, electric appliances that they will eventually make use of once they gain access to electricity. Thanks to all this information, I can stochastically derive load profiles, daily load profiles for the entire community. Once I have computed the potential load of the community, or loads if I want to work with the different scenarios, since I am dealing, of course, with uncertainty, because I am going to provide electricity to a community that never experienced electricity before. So it's not quite easy to foresee the actual load. So sometimes it's also good to work with stochastic approaches to take into account uncertainty of the evolution of the load. Once I have defined the load that I want to satisfy, through Microgrid Spy, I can understand what would be the optimal or cost optimal size of PV, for example, wind turbines or micro hydro, if such resources are available. If I need a battery bank, and how big was the size, and eventually some backup generators that could be biomass microturbines or diesel gensets, also depending on the availability of resources in that specific area. So by minimizing the net present cost, I will obtain a PV size, battery size, genset size, as well as fuel consumed throughout the years, and investment cost that I will need to face at the beginning of the project, and also the yearly operation and maintenance costs. So I will have a quite wide idea of what are the costs that I will need to face and technology I will need to deploy and how to use them in order to satisfy the load of the village. It's fundamental, in our opinion, that anyway all these mathematical process that we follow to size technology is strictly blended with the community, because only through identification of real needs of the community we are dealing with, we can formulate demand scenarios that are suitable, that make sense, and we can deploy technology in a way that will actually be used and accepted by the community. Otherwise, we risk to incur in to build technology that will not be used, that might be oversized, undersized, or simply not accepted by the community. So the first fundamental approach is needs identification through stakeholder engagement, particularly in the community, and data collection on the field. Through that, we can formulate realistic demand scenarios, assess locally available resources, because if I do not assess the locally available resources, I can say, okay, I'm dealing with sub-Saharan Africa, sun is for sure the most abundant resource, but I didn't realize I have a river running by, and some micro hydro turbines might have been way cheaper and more stable as a source of electricity. Only after that, I derive a system optimization that gives me as a result the optimal size and the optimal dispatch of technology. And through that information, I can identify the most suitable tariffs and propose a business model, again, with the community engaged. So as I was saying, the entire approach is people-centered rather than technology-centered. And we are not the only ones to say that. I mean, all the most important international organizations and NGOs build their strategy exactly on identification of needs. So every mini-grid or technology is deployed by first assessing what would be the productive uses or the human needs that are to be satisfied through the energy produced by the mini-grid. As my colleague was saying before, energy is just an instrument to reach human dignity. And first we need to understand what is needed by the population to get out of poverty, which services, and then we understand how much energy is needed to unlock those services. This allows me to enter the concept of comprehensive energy access planning. That is a concept we have developed in our group. So as I was saying, one of the main inputs of energy system models is the load demand. But how do I derive this load demand? Okay, I derive load demand, I have time series of renewable resources, and I get optimal capacity in LCOE. But what do I do? How do I derive properly the load demand? And how do I properly do resource assessment? And what do I do once I have costs and once I have identified a business model? So the core concept of the comprehensive energy access planning is that mathematical optimization alone is not enough. Modeling rural access to energy needs to follow a bigger path. Mathematical optimization is just one step inside a wider framework that allows me to really ensure sustainable development and acceptance by the community. And that's how the comprehensive energy solution planning was conceptualized. So as I said, we do not focus on kilowatts, but tasks that need to be carried out with these kilowatts, and human needs that needs to be satisfied through these kilowatts. And only through understanding the needs of the community, we then translate it into electric load demand that needs to be satisfied. And proper assessment of resources, as I said before, is fundamental in order to avoid waste of technology. Then, also identifying the proper solution. Mini-grid is not always the perfect solution. As I said, sometimes a standalone system or expansion of the national grid could be a better solution. So also asking yourself, what's the best strategy to follow is a fundamental step. And only once I have assessed that mini-grid is the solution I want to choose, I will proceed with the technical optimization, that is the optimization I introduced before. I will derive as an output from mathematical optimization sizing of technologies and costs associated to this technology. But providing an energy system itself will not be enough. It has been observed by several actors that only providing energy system might result insufficient to allow the local population to actually use this electricity. That's why we have understood that there is a set of ancillary activities, so parallel activities that are not strictly related with the deployment of the mini-grid, that help the community starting using the electricity, and in that way start the virtuous cycle of energy and development. So by providing, for example, access to microcredit, access to the market, and other categories of ancillary activities, we can foster the development process that energy alone is a driver of, but is not sufficient to activate. Once I have developed a business model that includes also this kind of parallel activities, I will perform an ex-ante impact evaluation. So I will ask myself, what will be the impacts of this strategy that I just designed? And if the impact actually answers to the needs I have identified in my first step, then I can consider to start my electrification process. Okay, this was the end of, let's say, the theoretical part of my presentation. Now, in order to get a bit more practical, I will give you some examples of studies we have carried out with the models I have talked to you about. So, for example, in this case, rural community in Bolivia, the mini-grid was wrongly sized because after just a couple of years, the community started to consume way more energy than the one that the mini-grid was providing. And we started to ask ourselves, why did this happen? So we performed analysis on the demand. We created different these different load scenarios, and we understood that the mini-grid was not correctly sized because they didn't take into account the fact that population might have started to grow economically, and with the economic growth bringing more consumption of energy. This was not had been taken into account, and the mini-grid was undersized. So through a proper planning of future scenarios, this could have been avoided by directly building a bigger mini-grid. Okay, so this is the approach we used. We defined different scenarios where the load was growing or not growing according to different parameters. Through this stochastic approach, we have as an output the sizing of a mini-grid that will be ready also to satisfy demand of scenarios with a higher load that were not taken into account by the developers of the mini-grid in the first place. A second example is when we slightly modified the model in order to take into account not only the fact that different scenarios of load might happen, but that in turns the electric demand evolves over time. So if the higher share of demand will be only after 10 years, let's say, of the building of the mini-grids, maybe it doesn't make sense to install all of the power in the first years. By properly assessing different scenarios of growth of the load, I can decide to postpone by 5 or 10 years, for example, the installation of a part of my technology. In this way, I can have a drastic reduction of the net present cost, because in year 0, I installed, for example, only half of the PV panels that I will need in the last year. And the second half, I will install it only 10 years after, when the population, when the community will have actually started using electricity, it will have been growing economically and will be consuming more energy only after some years. So also considering the time evolution of the load might allow me to better size my technology and save important shares of money. Okay, these are the results I was talking about. If I consider multi-year optimization, I can drastically reduce my net present cost. Another example is the sector coupling of the electricity sector that normal mini-grid deals with the heating part. Okay, so for example, in some communities, use of domestic hot water is important because temperatures can drop very low. If we consider during our planning phase and sizing phase of the mini-grid an interaction between the electric part and the heating part of the system, we can unlock synergies that otherwise would be unexplored. So if I connect a solar collector with my electric system, and I put a resistance that keeps the water hot thanks to the energy in excess from the PV panels, for example, I can be able to reduce by 30 to 40% the cost of my operation of the system, because I am exploiting synergies. I can store electric energy in the thermal side of the system and avoid using, for example, natural gas for heating the water during the night. Okay, so these are references that I used to build this presentation, and I would like to thank you for your attention. If you have any questions, I am open to discuss, and this is my email in case you have any doubts in the future.
Okay, if there are no questions for my colleague Nicolò, we can go on with the last part of today's presentation. But again, please, if you have any curiosity, even feel free to open your mic and ask, or use the Q&A section. Okay. So now it's time for having the eyes on the third layer of the one that we have been talking about so far. So let me share my presentation and tell me when you can see it, please. But I see a question. Okay, it was just some comment. Okay, now I think you should see properly the presentation. Can you give me a feedback, please?
Yes, we can see it, Nico.
Okay, so let's start. As I was saying, we are going to focus on the third layer, the so-called top-down mesoeconomic layer, in which we are studying the interconnection between the previous two layers with the rest of the economy. So today we would like to speak a little bit about one of the many possible applications of this kind of models. In particular, we are going to focus on the carbon emission reduction challenge, I would call it. And we will see how industrial ecology methods can help us in modeling this challenge. And in particular, we are going to see a little bit of one specific method, which is the environmental input-output analysis. So let's start. So this topic is probably very hot in many sense, and it's referred to the SDG number 13, climate action. During the recent months, we have seen many other countries joining European Union in climate-related challenges. In particular, we have seen Japan, South Korea, China, even if with different levels of commitment and also with different targets. Recently, we also have seen a combination of efforts between the most developed, well, let's say the economic powers of US and China. So, but why is so relevant to reduce CO2 emission? I would like to show you this website that you can navigate at the link that is here represented. And in this map, you can see the studies of attributional climate change events. When you see a red tag, you already know that this study has found some form of human influence on the occurrence or the intensity and the frequency of the event that is studied in that research. So the point here that I want to stress is that not all the extreme climate events are explained by human activities, but most of them are. So it's important to understand the deep connection between our activity today and emissions damages that will come in the future. But what is the magnitude of the problem? This is a very first important point to make because we can see a lot of effort and a lot of claims in reducing emission, but I think it's very important to have a perspective of what does it mean to drastically reduce CO2 emission at global level. I'm here reporting a study by Manfred Lenzen, who is a very important researcher in the field of industrial ecology, that came out with this paper together with his colleagues on PLOS One, trying to give an estimate of the impact of the pandemic that we are currently still living, sadly, during 2020. So through a model like the one that we are going to talk about today, they tried to have an idea of the impact of COVID. And as you can see, it was expected to have 4.5 reduction of CO2 emission during 2020. And what is really relevant to me is the fact that this reduction is the reduction that we would need every year if we want to go along this path of 1.5. So keeping the increase of temperature within 1.5. So that's huge. But what happened from the economic point of view? Also, they estimate this GDP contraction in this paper that was around 4.2. And what does it mean in practical terms? That if you take the pie of GDP, so gross domestic product, and of the world, and here you can see these very different colors representing the different economies of our world, that this reduction is like taking Germany out of the pie. So quite important reduction. Now, let me open a parenthesis on this work that was actually published during 2020. Now we are in 2022. We can fact check what Lenzen and colleague said in their paper, but more or less they were on the order of magnitude quite in line with the estimates that are currently today still updated, because this is a very difficult task to precisely know the impact on both greenhouse gases, so GHG, and GDP. As you can see, actually the reduction of emission was more important than expected, while the GDP contraction was a little bit smaller. And if you want, I'll leave you here also another interesting link in which you can have a estimate, a live estimate of the CO2 emission that are occurring all over the world. This website is called Carbon Monitor. And here is the source basically of this change that occurred. Again, you can see on the website all the details. In this picture, aviation is not considered, I think. And on the GDP side, the reduction was actually smaller than expected, but again, some changes are still on the process of being updated, and also the situation is so underdeveloped that it's very difficult to understand what is going to happen in the future. Okay, yeah, you can check the emission live if you Google Carbon Monitor. Okay, so coming back to this reasoning. So we have seen a very important reduction of CO2 emission together with a contraction of GDP that we know is the best measure so far to measure economic development. Is not perfect for sure, but is still what we use to measure economic development. So we see that this reduction of CO2 emission came with a very important reduction also GDP. But this actually not the main strategy to reduce CO2 emission. We are not supposed to reduce emission solely by changing consumption patterns. Yeah, because we have technological progress. In particular, in this specific challenge, what we can, the first indicator that we can start from is carbon emission intensity. I don't know if some of you know how to measure carbon emission intensity. Is a ratio, and that is comparing two measures. If somebody wants to try, feel free. But the ratio is between how much an economy emits in terms of CO2 equivalent, ton of CO2 equivalent, compared, so divided by the measure of the economic production, again, GDP. That is what happened in 3 countries that we take together with the green average for the world. On the y-axis, you have the years, and on the y-axis, you have the carbon intensity. So the kilos of CO2 emitted per every euro of GDP, measured in international dollars. And you can see a trend that is more or less decreasing for all the countries. And in particular, for China was very importantly decreasing. But as you may understand by yourself, the point was that GDP increased a lot, so the denominator increased a lot. While for the case of Italy, GDP is almost constant, and actually the decreasing trend is driven by a reduction of the numerator. So there are multiple ways actually to reduce the carbon intensity. At the end of the day, what we care is the total emission of CO2, obviously, but reducing this ratio can be good for the economy. But there is just one problem. The problem is that technological process is not spontaneous. So I put here this picture just to remember to ourselves that a more efficient plane doesn't come out of a less efficient plane like it happens in the natural world, okay? This process is not spontaneous. Technological change doesn't occur by itself. It is usually driven by, I would call it, 3 pillars of technological change, which is demand, investment, and policies, which are deeply interconnected. I would like to show you one particular technological improvement that is currently still happening, which is the one related to lithium-ion battery price. As you can see from this GIF, the reduction is taking place year by year, Now we have in the increase in prices and inflation that is global. So this reduction is mitigated by global effects, global problem on supply chain. But as you can see, since 2010, the reduction of CO2 was, not CO2, sorry, of the cost was around 90%. Okay. And that happened probably due to the fact that we are expecting an explosion in the demand of lithium-ion battery packages, okay? Mainly driven by passenger electric vehicles, but this is not the only application of this technology. And also, this increase in demand is probably very policy driven, because as we have seen, Europe in particular is pushing a lot on the reduction of CO2 emission in all its sectors, and therefore also in the transport sector. There are also other situations in which technology improved very importantly from the point of view of the cost per unit, and that is for sure the case of solar. You probably know that initially photovoltaic panels were the most practical way of producing electricity in space applications, because the sun was closer than it is from the Earth's surface, and also the production of electricity didn't require a combustion, which involved having an atmosphere. So at the beginning, the price of this technology was super high, way higher than reported in the chart that just came in the slide that is taken from our working data, in which you can see the price per megawatt hour of electricity of 5 different technologies. And you see that for wind, both offshore and onshore, the reduction is really important. And for photovoltaics is really amazing, I would say. And that occurred increasing the cumulative installed capacity. There is specifically a learning rate that is basically how much a technological unit cost is changing every time capacity doubles. And in the case of PV, it's one of the most, of the highest learning rate that we have seen in a technological field. As you can see, actually, the cost of other technologies such as nuclear and coal really didn't decrease, okay? For many reasons, we can talk about it if you want. But yeah, the whole point was to put on the ground all the, I think, important information to understand the connection between economic and environmental issues. And industrial ecology is studying exactly this, the so-called socioeconomic metabolism, in which we have 2 different spheres called the social sphere of causation and the biophysical sphere of causation that are overlapped, and in which we can find from our side the interconnection of our society, in which we demand goods because as human beings we have needs. We can find those products in markets, and the market are reached after industries have produced commodities. But in this process of production, industries are usually extracting resources from the biophysical sphere of causation, while probably most of the time releasing emissions in the atmosphere. So this connection is what we need to understand in order to find a way to limit, in this case, CO2 emission and reducing the annual amount of CO2 emission that we release as human beings every year. Okay. Economists agrees that the best way to do that, or at least one of the best measures to do this, is to introduce a so-called carbon tax. So putting a price on carbon. Okay, maybe it's easy to say put a price on carbon. We understand that there are externalities associated with the 1 ton of CO2 that is implying future damages, unpredictable damages. We don't know where, we don't know when. And so, okay, we know it's something that we should price, but finding the fair price is actually very difficult. Economists usually talk about social cost of carbon. So basically the cost of the ton of CO2 that is of this size, if you want to have an idea of what is a ton of CO2. And me and my colleagues as Italians, we usually have 6 tons of CO2 embedded in our consumption. What does it mean? It means that in order to guarantee the consumption of goods and services that we usually have in 1 year, we are responsible for 6 of these tons of CO2, each of us in Italy. But what is the social cost of this ton of CO2? It may depend on many things. First of all, the economic development that is expected by all the different countries of the world, it can impact the social cost of the additional ton of CO2. The same can be said also for the total amount of CO2 that we are expecting to release in the atmosphere, because this phenomenon is very complex and not linear in general, I would say. And also, super important, the damage function that we should assume is super relevant in determining this social cost of carbon, because of course, if the damage that is going to happen is going to be super high, also the social cost of carbon should be very high. Another important thing is the discounting. So basically, the price that we, well, actually the value that we give to future costs and incomes that will be generated. If we don't care about the future, the discounting rate is very high. So we don't give the same value to 100 euros today with respect to 100 euros tomorrow. And this can influence a lot because the damages are going to occur in the future, okay, not today. And also that can change importantly country by country. And there are also many other things that influence the social cost of carbon. Here I'm reporting a screenshot from another website that you can have access, and is basically the representation of Nature climate change paper that is here reported, and where the authors try to give an estimate of the social cost of carbon by country, taking into account different levels of uncertainty. And as you can see, there are a group of countries in this specific set of choices that are basically the same that we were talking about. Some countries can have benefits from an increase in temperature. Think about very cold places that currently are very hard for people due to the very low temperature. So maybe having 1 additional degree, if you think in a very selfish way, may be good for you. But of course, this issue is a global issue. And if you sum up all the contribution by country, you end up with a value of CO2 that is quite high in this specific set of inputs that were selected. Also, what I would like to stress is the differences that are there in this representation of CO2 emission per capita. Here I've compared the CO2 emission of 1 Italian and 1 Kenyan as you are. And this is, of course, just to point out that we cannot ask to countries like Kenya to be as concerned as we should be as in this case Italians, with the issue of CO2 emission, because we were responsible for most of the CO2 emission that now are determining the challenges that we start from today. Okay, we can have a discussion on this if you like, but I think it was important to underline this. So actually, since as I said, we are concerned with this issue as Italians, as Europeans, we are trying to do something for that. And actually, some jurisdictions introduced a price of carbon. And in particular, there are two main ways for pricing carbon. The first one is so-called carbon tax, in which you have a direct price associated with the emission of 1 ton of CO2, and is usually targeting precisely the price of the ton of CO2. And is ideally should go in the direction of the social cost of carbon, which is very hard to determine and very uncertain, as we said. Sweden was the first country to introduce carbon tax in general, and also the one with the highest price today, around 110. But as you can see, it may not be high enough if some hypotheses are taken on the social cost of carbon. The other way in which we are pricing carbon is the so-called emission trading systems. In Europe, we have the oldest one, and the target in emission trading system is the emission volume. So I say, okay, in this year, we can emit maximum this amount of CO2. And now I will give to my citizens, actually my industries, some permissions that will match at the maximum to this cap on CO2 emission. So actually the ideal word that is modeled behind this proposal is to have a perfect competitive market. So having perfect information. This is not happening because we don't really know what are the damages of the future. We know some other things, so it's not optimal, but is something. And in this moment in particular, the ton of CO2 are priced for 78 euros. This is changing very rapidly. But not only Europe as an ETS, China introduced 1 year ago now the first ETS, still with very low prices, but the amount of CO2 emission priced in some way is growing, okay? But actually, there are limits in carbon pricing policies. I would start from the first limit, which is low prices. That low adjective is very subjective, but for sure we can say that in this period in which the price of the emission permits for the ton of CO2 in Europe were below 20, they were for sure very low. As you can see here, this is a chart taken from the European Environmental Agency that is showing the electricity production in colors in different years, as you can see in the x-axis, for Germany, United Kingdom, Poland, and Italy. And on the y-axis, the left-hand side, you have the electricity production per technology. You have one color for every technology. On the right-hand side, we have the values of the verified CO2 emission in the black line. And you may notice something, that the only country that actually decreased importantly the CO2 emission in the power sector is United Kingdom. And you may ask yourself why. So the point is that in UK, while the ETS was still in place with very low values of carbon pricing, UK introduced the so-called carbon floor. And the carbon floor was basically a minimum level of price of CO2 that was around 20 euros. So quite more important with respect to the European one. And that was a very important message for investors, and that contributed. It's very hard to say that was the main reason, but for sure it contributed in reducing CO2 emission in that sector, because the investors, the owners of plants knew the fact that at the very least they would have paid 19 euros per ton. That is quite important. Another important things to consider is that we should treat this issue as a global problem, not having a local perspective. What we currently have is probably a local perspective. We will see why. Here you have all the CO2 emission embedded in trade reported for 2015 in this very interesting report. And you can see how the CO2 embedded in trade is flowing from one country to the other. And we are talking about 20% of global emission, not a small, tiny fraction of emission. And we should consider the interconnection between different regions in order to have, I think, a fair tax on CO2 emission. European Union is trying to address this. Ursula von der Leyen proposed in its own agenda the carbon border tax, which is basically a way to put the price on the CO2 that was emitted outside of European borders for something that then is consumed by Europeans. This issue is very difficult to be implemented, both from a political and technical perspective, but is something that is still debated and that experts expect to be in place if everything goes smoothly within 2026. So still a lot of room for improvement and time to wait. Okay. Okay, so we have seen again this possible limitation of carbon pricing policies. So if we want to model better or to test different alternatives that there can be with slightly different approaches, different levels of pricing, different total amount of CO2 that will be emitted by a certain jurisdiction, we should find analytical tools to do that, to model carbon policies. And here I am representing for you the industrial ecology analytical tools that are many, that are coming under the mantra of finding innovative solutions to complicated environmental problems. And there are many different issues that are important to be considered in industrial ecology. We should always have in mind that complexity and cross-sectoral analysis is fundamental. And not all of the tools has this characteristic, but among industrial ecology, both consequential and attributional life cycle assessment approaches can be said to be complex in selecting also the cross-sectoral sectoral analysis that is required for investigating these issues. I am reporting a bunch of models. Some of these consider time evolution. Some other also consider quantifiable forecast by different agents. So considering different agents with different utility functions. This is the case just of economic equilibrium models and system dynamics and agent-based models. And another important characteristic is the comparative advantage principle that is important in economic modeling, and this is considered by technology choice model. And also the possibility of having a high detail is very important in industrial ecology, because we, for many processes, need to go in very important details, but actually these are characteristics usually associated with attributional life cycle assessment approaches. In our case, what is enough for us is focusing on technology choice and input-output models that are actually very interlinked. But I display this to you so that you have also other inspiration in terms of different tools. Okay, so now we focus on one specific tool of the many that are offered by industrial ecology. And this tool is called input-output analysis. Some historical hints. This is Wassily Leontief. He won the Nobel Prize for Economics. And after a degree in Berlin and been moving to England, and then he worked for Urs, and then he moved to USA. So very multicultural working experience for Wassily Leontief. And during his period in USA, he was asked with this question: how much increase in mineral production, in labor demand, and in final consumption is implied by 10% increase in steel production? There was time of war, and the USA government asked him this question. And he realized that in order to answer to this question, he would have needed a table of interconnection between industries, because not only the steel production required for producing the final product is the one that you require, okay, in the supply chain as a whole. So he put together the first input-output table in 1941, and in 1973 he won the Nobel Prize of Economics for putting this together and finding a useful mathematical equations to have very today easy, because actually the math is not complicated once you have a very important computational power like our devices have. And today input-output tables are used to compute GDP. So quite important change in our society. But of course, this methodology has some assumption behind, and those assumptions are grounded on some principle that require, of course, some also limitation. And economy in input-output tables behaves in an ecosystem manner in which you have a material balance. So what is supply must be matched with what is used. Financial balance. So what is spent from one side is also what is received from the other side. And also one very important limitation is that technical coefficients are linear. So if you improve the efficiency of a process, you should update the coefficient that is otherwise always fixed. And so if you have to do 100 kilos of tomatoes or 1 million kilos of tomatoes, you always have the same structure, okay? Scaling variance. And that is consequent also in terms of price indices, okay? And to simplify, I would stop here with the basic assumption behind all Leontief input-output models. But what is an input-output table? That is the general structure of a table, and usually we work with multi-regional tables. What does it mean? It means that you can at the same time have a look at more regions. In this case, we have Kenya, Italy, and the rest of the world, so all the other countries. And first of all, we can find information on the technology, in particular in the red blocks. And here we have the information about the interconnection between industries of the same region. But actually, there may be also some Kenyan industries that maybe are using some Italian products. And in the pink blocks, you have the bilateral trade between industries of two different regions. And the same can be said on the final demand. So what I'm consuming, you are consuming, as private household. And also in this case, you can have consumption of domestic goods or consumption of imported goods. Okay. And another important layer of information that is provided by input-output tables is the so-called value added. So basically what people and owners of capital are providing in a sector thanks to their machinery, their hours of work, and also taxes are considered also value added in the light green part. But being the table an environmental input-output table, we also have the last piece of information that is related to economic activities that can be inflows or outflow, consider an extraction of resources or an emission of CO2, for example. So if we have the column of a specific sector, we will find across all those rows the information on what is required by that sector to operate in the period that is described by the table, usually 1 year. And on the row of the same sector, but on the row side, we will see where the output of this sector is flowing. So maybe some part is consumed by Italian industries, or maybe something is exported to rest of the world final consumers. Okay, this is the general idea of what is an input-output table. And what can we do with an input-output table? We can do environmental input-output analysis, taking advantage of its extended scope and its economic derivation. We can ask an answer to the question, how many tons of CO2 could be allocated to different regions of the world? That is what we can try to do together. So we define a geographical scope. We have an aggregation of the world in some regions. We just have one sector. At the moment, we don't care about the differences between different sectors. And we care about CO2 emissions. So once we define this input, we can have as an output the answer to this question. But actually, there can be at least two different answers to this question. First of all, the one called territorial or production-based accounting answer. So every country is responsible for the emission released within its boundaries. Like all the carbon pricing measures are today. And so from one side in the continuous line, take the example of China, you can have a certain level of CO2 emission. But if you consider the perspective of consumption-based accounting, in the case of China, the CO2 emissions that can be attributed to China are way less. Why? Because China is exporting a lot of its production. So having a consumption-based accounting means to give the responsibility, in this case for CO2 emission, for a country taking into account all the emissions that are released all over the world for producing what that particular country consumes. From the other side, take Europe. We release some emission, but actually we import many things that is implying CO2 emission in some other countries of the world. Okay. What we would like to understand is that maybe carbon leakage can occur if we have a production-based accounting in one jurisdiction. What is a carbon leakage? Carbon leakage is where emission decrease locally, maybe due to, for example, a carbon pricing initiative in Europe, like you can see here. But emission increase globally because maybe you become, as Europe, more reliant on import from somewhere else that maybe is producing the same stuff that you needed before having the carbon pricing, but they do it with a higher carbon intensity. We have seen what is carbon intensity, okay? So just to stress the concept, that is a contribution from our group that we did some years ago in the IEA report, pointing out precisely this. This was for energy, not CO2, but the principle is the same. When you have producer responsibility, you take into account exported goods and domestic consumption, while in the case of consumer responsibilities, or CBA, as you like, you take into account domestic consumption, but also imported goods, and not considering what you export. Okay? The point here that we want to make is that reducing pollution or CO2 emission in one country doesn't mean global improvement automatically. Okay? Because in order to check for this relation, we should have an analysis of the supply chain in different regions. So what we did in one paper that we did as a research group is basically asking ourselves, what would happen if in Europe tomorrow morning we switch from a production-based accounting method to a consumption-based accounting method? And in order to do so, since we don't have another planet to make the experiment, we need to create a virtual world, a model of the world. So that is where the modeling approach comes in. And of course, a model is always a partial representation of the real world. In particular, in this case, we take together multi-regional input-output tables, like the one we have just seen, with a linear optimization in what is called world trade model, a model that was developed by Faye Dachin, one of Leontief's students. And the model is behaving, simulating a so-called comparative statics. So tomorrow morning I get up and we have CBA or PBA. So there is no room for technological change. Not with the process that we have seen in the first slides is not allowed. What is allowed is to change production and trade patterns. So Italy can start importing more, or Germany can start producing for others. That is the only degree of freedom of the model. And what is regulating those choices is actually the principle of comparative advantage. That is based on the assumption that the first producer is the one that can do it at the lowest cost. And when it cannot produce anymore because resources are limited, the second more performant region that is producing that good will start doing it. Okay? The approach is taking a table as if it were a perfect representation of reality. We put this table under some constraint and equation that we see now. And after that, we have a representation of the world that should be good enough. And then we perturbate this world in introducing CBA and PBA policies more and more stringent, having an increase in the total cost, since the minimization is always the same and is here represented, a minimization of global cost. So I want to satisfy the demand of all the global population while minimizing global cost. And I cannot exceed resources. I cannot use more workers than the one that are living in the country, okay? And also, I cannot have negative values. This is more a mathematical constraint. But once we have this set of equation, we can simulate the CBA and the PBA that is becoming more and more stringent. And the results are the following. On the right-hand side, you have the CBA results. On the left-hand side, you have the PBA results. And the chart is the same. On the x-axis, we have the carbon budget of Europe. We are just imposing the policy in Europe. And the carbon budget is basically the total amount of CO2 that Europe can emit in the year that was simulated. And in this case, this reduction of budget is going from 1% to 40%, and is measured with the PPA accounting on the left-hand side and with the CBA accounting on the right-hand side, coherently with the policy that is in place. Of course, on the y-axis, we have the variation of CO2. Here we report it as a percentage. And the contribution of Europe, in the case of PPA, as you can see, is always decreasing and is also the same as requested. So here we have a reduction of 40%, that is just 6% of global emission, because it's imposed by the model. But what is happening? Interestingly, the rest of the world, ROW, is reacting, producing more for Europe, and the net, the black line, is actually going positive after a certain level. What does it mean? It means that carbon leakage is occurring with PBA if the constraint is getting more and more important. So if we want to reduce CO2 emission more and more importantly. On the other side, that is not happening with the CBA approach. And so the net is always decreasing because actually what is important here is the fact that CO2 on the supply chain is reduced, not local CO2. And that is true for the case of Europe, may not be necessarily true for other regions. Here you find also the disaggregated results. The paper should be online. If you want to have a copy, you can write me, I can send it to you. And I would like to thank you for your attention. I leave here my contacts if you want to send me an email or get in touch on Twitter or LinkedIn. If there are questions, I'm super happy to answer. Otherwise, I really feel free to write me if you like. Thank you very much.
Okay, perfect. Thank you very much, Nicola. Thank you also to Nicola and Francesco that presented previously. So I will share the screen just to have, let's say, a background for the Q&A session. I will start just from a comment that we received in the Q&A box from, no, sorry, it was in the chat actually, which is from Jemima Mooley, which like wrote that we are dealing with really complex topics, and probably that also the participants to today webinar will need time to synthesize it, to deep dive into it. So I will start this Q&A session like suggesting to our attendees to write us if it's me, and I can forward it to our partners, or you can write directly to them since they shared their contacts. So if you want to deep dive, as also Nicola was pointing out, we can let's say direct you to some literature in which you can have further analysis on the topics that were touched today. So, so that was it. If you have question, again, if you want, you can write in the Q&A box. Otherwise, you can raise your hand and I can give you the floor. So yeah, we are here available for a few minutes. Otherwise, feel free if you think that today you are not able to have, let's say, very articulated question because the topics were really, let's say, complex. Feel free to send them with a synchronous, let's say, manner, sending us an email. I don't see actually any question or any raised hand. So maybe just 1 minute. And otherwise, if no, let's say, question is or no hand is raised, I would close here the session. And again, thank our partners that provided managed to provide today's lecture, which was, I think, really interesting and really future oriented. So really, thank you. Okay, I don't see any questions, so thank you very much, Nicolò, and Francesco. Yeah, just a quick reminder also for the attendees, as soon as possible, we will upload on YouTube today's recording. So again, if you want to watch it again and focus on specific part that you weren't able to follow during the presentation, feel free to do it and write us if you have any doubts. So thank you very much. Have a nice day, and see you on Thursday with the Imperial College lecture on, again, the, let's say, some real cases on modeling in real world. Thank you very much. And again, have a nice day.
Thank you. Bye.
Thank you very much.